Okay, so in this video we're going to talk about integration by parts. So as always, let's start off by looking at the formula. Where u and v are values we have substituted in order to give us a simpler expression in terms of our variable. So what does that mean exactly? Let's take a look at an example. So if we are asked to evaluate the integral x times the cosine of x with respect to x, straight away we can see that we can't use integration by substitution that we saw in the previous video, because we don't have an expression which contains a function and the derivative of its function. So in order to use integration by parts effectively, the trick here is to pick a u value that when you differentiate it becomes easier to handle in terms of the variable you're looking at. So for example, if we pick the cosine of x as u and then we differentiated it to minus sine of x, this expression is not going to become any simpler to handle. However, if we choose our u value as x in this example, the derivative of x with respect to x is just 1. So this expression will become much easier to deal with. So let's do it. If we say u equals x, then if we take the derivative of u, du by dx, we have du by dx equals 1, therefore du equals dx. In this example, it's possible to treat derivatives, so du by dx equals 1. We can treat them similarly to fractions, so du equal to dx if this is a simple fraction. And next we need to pick a dv value. Now we don't need to worry too much about this becoming more simple or difficult to handle, because we don't see its derivative used in this side of the expression. So if we say dv equals the cosine of x dx, so that's what we have left when we've taken out our u value. If we integrate this, we can directly integrate this. This is equal to the sine of x. So now we can substitute our values back in. So on the right hand side of this formula we have uv, so that would be x times the sine of x. So x times the sine of x minus the sine x, du is just dx, so we have sine x dx. And then our last step is just to evaluate this integral. So now we have x times the sine of x minus, and the antiderivative of sine of x is minus cosine of x. So this negative sign will change to a positive, so we'll have plus cosine of x. And as always with indefinite integrals, we need to add a constant of integration, plus c. So you can see how sensibly choosing our u and dv values, we were able to simplify this expression a lot in order to give us a solution. So let's now look at a more complicated example. Okay, so in this example, we're asked to evaluate a much more complicated integral. So as I mentioned earlier, we need to find a u value that when we differentiate it, it becomes a simpler expression. So if we used e to the 3x in this example, the derivative of e to the 3x is 3 times e to the 3x, so that never becomes simpler. However, if we choose x squared, the derivative of x squared with respect to x is 2x. So we reduce this polynomial by a factor of 1. So we have x to the 1, which is simpler to deal with. So let's do that. So the derivative of x squared with respect to x it's going to be 2x dx. And again, the reason this dx is here is I've just brought it over from here. Instead of having du by dx equals 2x, I've just written it as du equals 2x dx. And then our dv value would therefore be e to the 3x dx. So if we integrate this, we have v equals, and directly integrating, as we saw in the previous video, we'll have a third e to the 3x. To simplify the problem, we just add the constant of integration at the end when we're finished. So following on from our formula, we have is equal to u times v. So we have x squared times a third e to the 3x. So we have x squared over 3 e to the 3x minus the integral of v du. That's the integral of v, so the third e to the 3x du times 2x dx. Then if we simplify this, we have x squared by 3 e to the 3x minus, and as always we can pull out the constants here. So we have a 2 on the top and a 3 on the bottom. So if we pull that out, we have 2 thirds times the integral of x times e to the 3x. X times e to the 3x dx. And you might be thinking here that this expression is no simpler than what we had before. However, if you take a look at this integral, we can use integration by parts once more to simplify this even further into something we can directly integrate. So you'll notice how x was to the second power here, and now it's to the first power here. So if we use integration by parts one more time, this should give us an expression in x to the 0th power, which we can directly integrate. So now we've got a bit more space, let's focus on the part we have here in yellow. So again, by choosing sensible values of u and v, we'll be able to simplify this expression even further. So once again, we want to choose a u value that will simplify somewhat. So if we choose u equals x, we have that the derivative du by dx would be equal to 1. So dx can come up here, so du equals dx. Then our dv value is therefore e to the 3x dx, and then we can integrate that to give us v equals a third e to the 3x from the reverse chain rule. So by using the formula, we have this is equal to uv, so x over 3 e to the 3x minus the integral of v du. Which means we have a final solution for this part underlined in yellow, which is still our x over 3 e to the 3x minus, by integrating directly and using the reverse chain rule, minus a 9th e to the 3x. So let's bring that all together now. So since the yellow part is just an aside, this equal sign now leads to this equal sign here. So we're left with x squared over 3 e to the 3x minus 2 thirds times the value we found in yellow here, which is x over 3 e to the 3x minus a 9th e to the 3x. So now all we need to do is simplify this expression. And you'll find when you perform that simplification, that will give you e to the 3x over 3 multiplied by, we have x squared minus 2 thirds x plus 2 ninths as always, since we started off with an indefinite integral, we need to add our constant of integration plus c. Hopefully this video has helped you to understand integration by parts a little bit more. As always, if there are any questions, feel free to pop them in the comments box below. If there was anything in this video that you didn't understand, I would encourage you to pop over and have a look at my calculus playlist, where I've uploaded videos on a wide range of calculus topics. I'll see you in the next video.